biochemistry, we can learn a lot about various molecules by measuring both the light that they give off, luminescence, as well as the light that they steal, the light that they absorb. And so when molecules absorb light that we can normally see, we see color. We get colorimetric readouts. Whereas if we can then extend this idea to absorbing light that we can't normally see, like UV light, then we can actually and use a machine to measure how much of that UV light gets stolen, then we can do the same sort of thing to get information about molecules based on what they're absorbing. And so it can get kind of confusing that in both of these, or I guess all of these cases, we're talking about light. But in the case of like a luminescence, something like fluorescence, where the molecules are absorbing light of one wavelength and giving off light of another wavelength, there we're actually thinking about the light that's being given off. Whereas with the colorimetric methods, with the UV-based methods, there we're measuring a light that's getting absorbed. And so these are key concepts to keep in mind. And now let's dive into the details. Sorry, but in some places I kind of mix the terms transmission and emission. So transmission is when you have like some light coming in, and then some of that light gets stolen by the molecule, it gets absorbed, and then you have some light coming out. That light is transmitted. There's also emission. This is when a molecule like gives off new light. So it's not the light that was coming in, it's like light of a different wavelength. And so if this can actually, like with fluorescence, it would be like you would have a higher energy light coming in, then you would have a lower energy light given off because the molecule would absorb some of that light. So that light would be missing in the transmission. But then this molecule, so the electron gets excited, we'll get into this, then it's gonna kind of fizzle back down. It's gonna not be totally efficient, so it's going to lose some energy, and so you'll have a lower energy, longer wavelength light given off. That light is being emitted. It's not the light that came in, it's like a different wavelength. Then you can also have light emitted when the electrons are excited from sources other than light. And so emission doesn't even have to involve light at all in the excitation phase. It can be from like a chemical reaction or something like that. So absorption, light that comes in is stolen. The light that remains is transmitted. If you have light that's actually given off anew, light is emitted. And so with fluorescence and luminescence and stuff, we're measuring emitted light. And with dye-based methods, we're measuring the absorbed light. Or we can measure the transmitted light, which would be the absorbed, like all that was coming in, the incident wavelengths minus the absorbed wavelengths. So sorry I kind of messed the terms up sometimes, but that is the correct terminology. And if I use it a different way later on, I'm sorry, and please try to remember that this clarification that I have here.
Let's just step back and think about what light actually is. So light is just these little packets of energy called photons that are traveling in waves. If we think about visible light, this is just a tiny little portion of the electromagnetic spectrum. So electromagnetic radiation, or EMR, is just this term that describes these little packets of energy traveling in these waves. And different wavelengths have different amounts of energy. So, or I guess it's easier to think in terms of I find it easier to think in terms of the energy. And so the more energy you have, the faster you're going to go up and down wise. And so like the more wavelengths you're squishing in to a single distance. So all light travels at the same speed, the speed of light. And so in order to keep that relationship, if you have more energy and you want to travel more, you're going to have to go up and down more times. So you have a higher frequency. And to keep the same distance, you're going to have a shorter wavelength. So higher energy photons, higher frequency, and shorter wavelength. And if we go really, really high, we get things that we can't see with our eyes. We get ultraviolet, we get X-ray, we get gamma rays. And if we go really, really slow, we get really long wavelengths, we get things we can't see. Infrared, microwave, radio. But in that sweet spot, our eyes are able to detect this visible light. And if we think about white light, that's actually a combination of all of those different wavelengths that we can see in this visible light range. So RGB, the red, orange, yellow, green, indigo, violet, or blue, indigo, green, blue, indigo, violet, RGB equals white. And so if you subtract one of those things, then you're going to see a color. And this is why things look colored, is that they're absorbing light that we can see, and then the light that the rest of the leftovers is going to look different. Molecules can also absorb light that we can't see. And this is the same kind of concept as if we're using something that's colorimetric, so something that has a readout that we can visually see. Except there we can't see it with our eyes. We can often measure it with some sort of spectrophotometer thing. I can never say that, spectrometer. One of those machines that you can like stick a cuvette in, or we can have a UV detector on like a nanodrop machine, various things like that. And this is going to allow us to quantify the amount of those wavelengths that are absorbed. And they can be wavelengths that are absorbed in the visible range or wavelengths that are absorbed in other ranges. And so often when we're talking about biological molecules, we're looking at the absorption of UV light because proteins and nucleic acids tend to absorb ultraviolet light. And so we can measure UV light in order to think about, get information about the concentrations of the various molecules. Sorry, I'm looking for that slide and I can't find it in this set, but light absorbs wavelengths, or these molecules will absorb in the UV range. And then before we can use we can actually use this thing called the extinction coefficient to figure out exactly the concentrations of these molecules based on how much of the light that they are absorbing. I'm using this thing called the Beer-Lambert Law, and I go into this in more detail in other posts. We can also use methods that involve the binding of various dyes to a protein. If these dyes then change color, a common thing we do is this like Bradford assay, which uses Comasi Brilliant Blue. This dye is going to bind to proteins and change its color. And when it changes its color, then we can measure the absorption at that changed color. So measure how much of the light is being absorbed at the wavelength that will give us this color. And so remember, what you're seeing is the missing wave, is like that combination of light that's left over when you've removed something. And so when you remove something, you're left with the leftovers. And so although you're seeing one color, although you're seeing this bluish color, what that actually means is that you're absorbing in this more like yellowish color. And when you see the version that's not bound to proteins, it's going to look more brownish. And that's because it's absorbing more of this bluish light. And so you have to remember that when you're thinking about dye-based methods, you're absorbing at the wavelength, not the wavelength that you see, but the wavelength that you don't see. And because you don't see it, because it's getting stolen by the molecules, and different molecules will have different wavelengths that they absorb, and therefore different wavelengths that they look like they are, that we see. And we can take advantage of this to measure different wavelengths of absorption and get information about different types of things. The reason why the molecules are absorbing different wavelengths, and the reason why, say, the Bradford is going to change its color when it binds to a protein, is because the wavelengths that a molecule absorbs depend on the molecule's molecular structure and its electronic structure. So all of these molecules we're talking about outside the scope of this post, but they're made up of atoms, carbons, hydrogens, oxygens, etc. And those atoms are joined together by sharing pairs of smaller molecules called electrons. These electrons can live in various places in these molecules as places they like to hang out more. And these can occupy different energy states. The key thing to know is that electrons can absorb energy and move to a higher excited state. And they can also then release that energy back, and they can release it in different ways. Some of these will give off light, which we see in luminescence and fluorescence. And sometimes they'll just kind of fizzle out or give off heat or bump into other molecules. But because they can only live in that excited state for a little bit of time before they fall back down. But the amount of energy it takes to get to an excited state is dependent on the molecular makeup of the molecule. So different molecules in different parts of the same molecule will have different perfect amounts of energy that they could absorb to get excited. This amount of energy can differ than if the molecule changes its environment or the molecule itself changes. And so, for example, in the case of the Bradford assay, the dye is going to get stabilized in a different, state, a different charge state, and this is going to change what wavelength it likes to absorb. And for technical reasons that I'm not going to get into here, molecules that have a bunch of rings, this thing called electron delocalization or conjugance or resonance, basically it is going to lower the cost that it takes in order to get to an excited state. And for this reason, it's going to lower this amount of energy, and for this reason, it's going to make it so that it's more likely that the light in the visible range will be absorbed. So if we think about these light ranges, so molecules that we care about, like proteins and care about in biochemistry, like proteins and nucleic acids, they're typically going to be absorbing in the ultraviolet range. We can't see if they take light in the ultraviolet range. We need special equipment to see that. But we can see that if they absorb in the visible light range. So if we need to get them to absorb a light that is at a lower energy. And so to do this, we can lower the cost of, we need something that has a lower cost to excite that electron. And this often happens when you have that conjugate, so when you have that resonance on that electron delocalization. And so for this reason, when you have molecules that are made that have these ring structures, you're often going to have a colored product. And so this is why like dyes and pigments and things, they often have a bunch of rings. And if you can increase the amount of like electron sharing and stuff through some sort of chemical reaction, say, then this can create a colored product from a product that wasn't colored before. And so there are lots of different ways that we can use a colored readout. Sometimes we'll have just something like it changes the charge state of a molecule. Other times we'll have actual reactions that are going to make a colored product from like other non-colored products. So there are various ways and times that we use different colorimetric methods in biochemistry. We also take advantage of methods that involve giving off light, so things like fluorescence and luminescence. And so basically in these cases, the electron's getting excited and then it's getting released, but when it gets released, it's going to be giving off light. And so here we can measure the light that's given off. And so here we're measuring like the emission. Before, when we're measuring like dye-based methods and colorimetric methods, we're measuring the absorption. Here we're measuring the emission. So we're measuring the wavelength that you're actually kind of like seeing, rather than the things that's getting stolen. And typically, there are various methods that we can use, and there are different names for luminescence when it comes from different sources. And so luminescence is just when you have light that's given off when an electron gets excited and then falls back down. We can excite that electron in various ways. One is by giving it energy through shining light at it at a wavelength that it likes to absorb, and then measuring the wavelength that's released. And this is called fluorescence. The energy can also come from different sources. So it can come from like a chemical reaction, in which case we call it chemiluminescence. It can come from a biochemical reaction, and we call it a bioluminescence. So we're thinking things like luciferase, which we talked about yesterday. And so all of these involve giving the electron energy, this energy, so it absorbs something. The absorption is coming from light. Then we call this fluorescence, and when we're measuring the light that's given off, this emission. And so often, typically you want to have it so that the absorption, for a good fluorophore, you'll have the absorption and the emission greatly separated, so that you can then measure, you can shine light at the wavelength that it absorbs, and then measure at the wavelength that it emits without just measuring the wavelength that it absorbs, because you're shining that light at it. And so that's the idea with fluorescence, is that you're measuring the light that's actually being given off. And remember that this is different than when we're talking about luminescence. This is different than when we're talking about color. When we're talking about color, or to an extension of when we're talking about like UV absorption, here we're talking about absorption. So we're measuring what's getting stolen. And remember that what you see is the absence of the thing that's stolen. And so in the UV case, you can't see a difference because you can't see the UV light to begin with. But if you could, like if you were the machine that you were using to measure, then you could see that light was being stolen. So you can measure the absorption. And then if you use like the Beer-Lambert law, you can directly correlate that to the concentration of the molecule, because the more you have of the thing that absorbs the light, the more light that's going to get stolen. And therefore, there's this direct relationship you can use, and different molecules have different amounts of light that they'll steal for like copy and things. So like in terms of their molarity, so how many copies they have. And then you can use this, each molecule will therefore have this extinction coefficient you can use to convert between the absorption and the concentration of that molecule. And so this comes in really handy when we're trying to figure out the concentration of various proteins. And you can find the extinction coefficient for a protein of interest if you have like a really pure protein, using this tool called like Spacey-Prop program, which I've talked about before. And then you can also use methods that will give you a color-based product based on how much of a thing is present. Same sort of idea, except here you're using things that you can actually see. And then you have fluorescent-based methods that will let off light, and then you're measuring the light that's let off. And so it's really important to keep in mind that you're measuring these different things. So you're measuring the transmission, you're measuring the light that's actually given off when you're talking about fluorescence. So you're measuring this. Whereas in the case of absorption-based methods, you're measuring the light that's actually stolen. This is going to, and if it's a color-based method, this light will be opposite of the color that you actually see on the color wheel. And so, so that's just something to keep in mind. These terms can get kind of confusing when you're thinking about what's being absorbed, what's given off, and kind of the relationship, how UV is really just an extension of this whole like GVIV thing. We just can't see the difference with our own eyes. We have to use special equipment to do so. But when we do, then we can, it can be really useful. And so, hope this helps.